Hi, today's lesson will be on dividing radical expressions. So, previously you learned the product rule for radicals. Now we are going to introduce the quotient of radicals rule, which basically says that if you have the square root of a quotient, so remember that a quotient is basically a ratio or a fraction, that you can simplify it by taking the square root of the numerator and dividing by the square root of the denominator. So if you take a look at the first example, the square root of 25 divided by 49, we can separate that into the square root of 25 divided by the square root of 49. Since both are perfect squares, we take the square root of each and we get 5/7 as our final answer. So that's pretty simple there. Well, now let's take a look at a new one. So simplifying by a quotient isn't too hard or different. What's different is learning to rationalize when you have a radical in the denominator. So let's talk about that instance. So here I'm asking you to simplify the square root of 25 thirds. If we can reduce this on the inside, we always should. But in this case, we can't. They do not have any other common factor other than 1. So what we want to do is separate our numerator from our denominator and simplify them separately. When we do so, because the square root of 25 is because 25 is a perfect square, the square root of 25 is 5, but we cannot simplify the square root of 3. Normally, we would say, well, there's nothing else that we can do. But this is not the end. If you look at the paragraph on the PowerPoint slide, it says that this does look similar to our previous example, and that's true. Our previous example was the square root of 25/49, so it looks similar to that. But the reason we're going to call this the wrong answer here, 5 over the square root of 3, is because our denominator contains this radical sign. So when we simplify radicals, a quotient with a radical, it is considered incorrect or not customary if we leave the radical. So why do we have wrong in quotes? This issue is going to matter now in this course and throughout your high school career, but if you get to calculus, you won't have to worry about eliminating the radical. So this is similar to how in elementary school they might tell you do not leave a number as an improper fraction. Remember that an improper fraction is when a numerator is larger than its denominator. So they would then ask you to convert this to a mixed number where 7 goes into 9 one time. 1 times 7 is 7, and when you subtract you get remainder 2, meaning that this value as a mixed number is 1 2/7. So 7 goes into 9 one time with 2 left over. But now that you're in high school, it's perfectly fine to leave things as an improper fraction, and in fact, it's even preferred. So while we'll call this the wrong answer for now, technically it is correct. If we were to type in our calculator the square root of 25 thirds, and then type in 5 divided by the square root of 3, we would get the same answer. But for the purpose of this course, you have to learn a process called rationalizing the denominator. So we'll show you how this works in the next slide. So if we take a look at our answer here, 5 over the square root of 3 from the previous example, we recognize that there is a radical in the bottom. So for step 1, it says we need to multiply the radical expression by a, quote, convenient 1. Well, this convenient 1 is going to be a number that when multiplied by this square root of 3 will give us a perfect square, so that when we take the square root of it, we will not have a radical. So if we think, well, what number can I multiply by 3 to get a number that is a perfect square? Well, 3 is a factor of 9, which is a perfect square. If we take the square root of 9, we would get 3, and that would give us a desired result to eliminate the radical from the denominator. So what is it that we need to multiply by the square root of 3 to get the square root of 9? Remember, we've covered multiplying radicals, which says that you can multiply radicands. So if I multiply this square root of 3 by another square root of 3, that results in a square root of 9, the square root of which is 3. We call this a convenient 1 because the value must equal 1. So we'll call this a big, nasty 1, meaning whatever is on our denominator must also be the same in our numerator. Why? Because any number divided by itself equals 1. Recall back to just dividing a number like 5 divided by 5 is going to equal 1. Well, the square root of anything, such as the square root of 5, if we divide that by the square root of 5, it will also equal 1. So this is our convenient 1 referred to in the PowerPoint slide. So we're not really changing the value, we're simply using this 1 to get rid of the radical in our denominator because it gave us a result that was an integer, meaning just a positive or negative whole number here. So our next step is to simply multiply our numerators together and denominators together once we determine the convenient 1. So when we multiply 5 times the square root of 3, remember we can only multiply radicands together and numbers by themselves together or outside of a radical. So all we'll simply do is place the 5 beside the square root of 3 as a product. So now that we've already taken the square root of 9 and we know it's 3, we're going to include here and just move over our numerator 5 square root of 3. And our final answer is 5 square root of 3 divided by 3. So keep in mind that 25 square roots of 3 is equal to 5 square root of 3, but it is not customary to leave a radical. So the process of rationalizing helps us to eliminate that radical, thereby giving us a final customary answer of 5 square root of 3 divided by 3. So now if we try a couple more, we will notice when looking at this problem that we again have a radical in our denominator of the square root of 3. We cannot reduce anything here on the outside. If we could, we would. It would help us out. So what we're now going to do is multiply by our convenient 1. So actually I'm going to change that equal sign to a times. Similar to the previous example, if we multiply by the square root of 3 again, that will actually give us the square root of 2 of our 3's, which that is our point. Because our index is 2, we want to end up with 2 of the same factors. So the square root of 3 times 3 is 3. And that should always be the case, that when rationalizing a expression with a square root in the denominator, we want to end up with 2 of the same factors. So it will usually be exactly what you see here, the same thing that we see here. However, we don't need the 7. So the square root of 3, of course, when we use it on the denominator, we must also use it in our numerator, so it will equal 1. So now we want to simply find the product of our numerators and our denominators. When I multiply my denominators here, I still have my 7, but now I have the square root of 9, with the square root of 9 being equal to 3. So 7 times 3 is 21. So the more you understand this, you will be able to find out some shorter steps to do this. Continue by multiplying your numerator. So we're going to have 2 times the square root of 6 times 3, which would give us 2 times the square root of 18. What I want you to keep in mind before deciding on your final answer is if this 18 under our radical can further be simplified. If I take the 18 and break it down into 9 and 2, I recognize that 9 is a perfect square. So the square root of 18 is 3 times 3 times 2, or 3 square roots of 2. I do, however, need to bring down this 2 I already had that is being multiplied by the square root of 18 and multiply it by 3 square roots of 2. When I do so, multiplying these numbers gives me 6 times the square root of 2. That number I will then place in my numerator. So I have now completely rationalized my denominator, meaning I've followed the process to eliminate the radical. And the last thing I should do is determine if I can reduce this. One thing to keep in mind, I'm sorry, that should not have a 1. That should just be 2. One thing to keep in mind is that you cannot reduce numbers under the radical with numbers outside of a radical, or not having a radical at all. But you can reduce the numbers on the outside here. So if I consider 6 and 21, I might recognize that my factors for 6 are 2 and 3, and my factors for 21, 7 and 3. Sorry about this. So 6 divided by 21, having a common factor of 3, would leave me with 2 on the top and 7 on the bottom. So all I did was reduce 6 over 21 to get 2 over 7. And of course I carry over my square root of 2. And I have now reached my final answer. So taking it step by step, we need to rationalize by multiplying by our convenient 1, multiply our denominators across, multiply our numerators across, determine if we can reduce anything in a radical, which we could, and then finally looking to see if there's any numbers we can reduce outside here. And remember, we always want to verify in our calculator as well. All right, and lastly, let's try B. For B, we have 5 divided by 4 times the square root of x. So this isn't really much different from problem A, only this time we have a variable. So remember, if we want to get rid of our radical, we need to create a perfect square. So what I want you to think is, what can I multiply by here that will give me just the x? So of course I keep my 4, but if I multiply by the square root of x, I would then have the square root of x times x. Since I have a pair, my index being 2, it comes out, leaving me with 4x and nothing under the radical, which should be the point. You want to get rid of what's under the radical. Now, again, anything I multiply on the bottom must also go up top. Why? So that this has a value equal to 1. And then I simply multiply my numerators. So that gives me 5 square root of x. And then I'm going to carry this over because I cannot further simplify it, leaving me with 5 square root of x divided by 4x. And we will stop there.